Okay, we're recording. All right. Welcome, everybody. My name is Chris Rocky. I'm the district hydraulic engineer. We just finished talking to you about interception calculations, and now we're going to talk about the hydraulic grade line calculations, or how do we size the pipe. We're going to size the pipe so we know we have the right size and material to use. I'll go ahead and share, and we can start on that. There we go. Um, So we have our standard cross culvert. We're trying to get the hydraulic grade line to stay down in here just through the culvert. What we don't want to do is have this end up rising up to a level that becomes a problem. And again, we're with the spreadsheets. This spreadsheet, we're going to collect all the information that we're going to need to use when we go into Culvert Master to input the data that we need for the results. And then there's a location here where it has the results from Culvert Master that we're going to type in. Going through the spreadsheet, they're very similar to others that we've talked about. System number, inlet. I've split this one up for this discussion. We're talking about only this line right here, 1B. The one with drain system number 2 has many drainage inlets, and we'll talk about that in the next presentation. And then how many, the drainage inlet that you are, addresses the culvert that you're interested in. And then the Q, we're gonna need to provide the flow for the 10-year and the 100-year storm. The 10-year storm, well, we'll talk about that in a few minutes, but we'll need to do two spreadsheets, one for the 10 and one for the 100. And during the last break, I attached the spreadsheets to the meeting invitation, so you should have access to those now. Type the size of the culvert, type in the material, the length of the culvert, and then it calculates the slope automatically for you. And then the inlet flow line elevation and the outlet flow line elevation. I try to use the elevations straight out of culvert or straight out of the surveys, but if for some reason those elevations are not available, you can assume elevations. It doesn't have to be the natural ones out of surveys. And then the available headwater, we'll talk about that in a moment. And then the computed headwater is the answer that we're looking for, and it's going to compare the computed to the available and give us a check. And if it's okay, then it's less than. If it's more than, then we'll get a little error message. And then we'll use the critical depth in our calculations and then using the tailwater elevations. So going to the next one. We're interested in the headwater elevation in two locations. For the 10-year storm, the headwater cannot rise above the soffit of the culvert. For the 100-year storm, the headwater cannot cause objectionable backwater. And what that means is if you don't want it to spread into the traveled way. So pretend that you put a plug in this culvert and we let the water rise up until it becomes a problem or it flows away. And at that point, we have the objectionable backwater or headwater elevation that we're looking for. Usually we're looking at the ETW. We don't want it to spread into the traveled way, but we can't forget to turn around and look out into the field because there might be somebody's home that is lower than ETW, and that would turn into the maximum elevation that we could use for the 100-year event. And then another scenario that I didn't draw in here would be is if we had like a V ditch right here, then the elevation is going to be the elevation of the V ditch because the water will come up to that ditch and then go on its way to the next location. So you're looking for what's called the objectionable backwater or objectionable headwater, and put a plug in the culvert, let the water fill up until it becomes a problem, and that is the elevation that you're looking for. Usually you have the elevation at the flow line here, and you measure the difference in the field between this elevation and this elevation, and then just add it to it, and that becomes your headwater elevation. So you'll eventually need to go out and look into the field and take a look around. It's awful easy and very tempting to just go to the design cross sections and grab the ETW elevation and use that. But there are many other contributing factors, and really the appropriate way to do it is do a field review and go out and look at this location and measure these yourself, or some other person that you're working with. And now looking at the other end of the pipe, we have to consider the tailwater elevation. So if it's like this purple one here where it just falls right out and it doesn't create any kind of a backwater condition, then the tailwater elevation will basically be 0. And then we're going to end up using the critical depth from our calculations. And then we'll take the existing flow line elevation right here and add the critical depth to it to get the elevation for the tailwater. That's probably the one you'll use most often. However, sometimes when the water comes out of the pipe, it has to overcome a hole. It has to fill up a hole or something like that before it can travel on and go away. And if that's the case, then the tailwater elevation is up here. And again, you want to grab this you want to measure the difference between the flow line elevation at the outlet and the elevation here and add those together, and that's the number you'll be looking for. So in the, let's go on to the next one. All right, start Culvert Master. And in Culvert Master, when it comes, again, it comes up with a dialog box, and you need to close, you can just close out that dialog box. There's nothing in there you really need to focus on. And then we'll come over to the quick culvert calculator. This title, worksheet title, is going to be the title that ends up at the top of your report. So you might want to put in here drainage system 1 and then the letter of the pipe. For example, the culvert letter might be B. So drainage system 1B, and then either proposed or existing, and then what storm event, 10 or 100 year. And this is editable at any time, so you can use anything you want and come back and change and rename it anytime you're ready. And you can see right here, it's calling it worksheet 1 up in the corner, and then it gives us a nice dialog box. The Culvert Master and Flow Master programs are pretty intuitive and pretty easy to get through once you've walked through one of them. They all work pretty similar. Headwater elevation, discharge, and size. We are concerned about the headwater elevation. So that's the one you're going to be calculating for 99% of the time. The discharge, again, is the Q. You're going to have the 10-year or 100-year storm that you're going to use. Maximum allowable headwater, that's the, no, there's something we didn't see first. Let's go back to this. The available headwater that we talked about on this spreadsheet, the available headwater for the 10-year storm is the soffit of the pipe. So this elevation right here is just a calculation that takes the inlet elevation and then adds the size of the pipe to it, and that gives us the 10-year storm elevation that we need. And then the critical depth for the pipe, we have the tailwater elevation here. The first iteration through, you're going to use the outlet elevation. And then after you get the first iteration, you'll pull up the report, you'll get the critical depth, and then that'll add the critical depth to the tailwater elevation, and then that's the number you'll use for the final iteration. So going back to Culvert Master, the maximum allowable headwater, so for the first iteration, you'll use just the flow line elevation at the outlet. And then after you do the first one, then you'll add the critical depth in, and then come back with one more try and change that to the final elevation. The tailwater elevation, that is, excuse me, I got that mixed up. The tailwater elevation is where we add in the critical depth. The headwater elevation is straightforward. It's either the soffit of the pipe or the top of the culvert, or the objectionable backwater elevation, depending on what storm event. And then the type of pipe, circular, material, concrete, size, probably 18-inch. For the calculations that you guys are doing, if you have an 18-inch pipe and it's being resized down to with CIPP, you could go ahead and assume that's an inch and a half thick or so. And I saw 15-inch was one of the options, so you could probably use that one, and that would be okay for you guys, and to have to avoid trying to do a custom size. And then the number of barrels, is it one pipe or is it two pipes side by side? Culvert Master is limited in that it can model two pipes or more side by side, but they have to be the same design parameters, the same length, the same slope, the same elevations. It does it all at once right here. So most likely you'll have one culvert, and then for example, if one culvert doesn't work at your location and increasing the size doesn't work for some reason, then you can increase the number of culverts side by side. And I've had to design as many as 5 culverts side by side before. And then the Manning's N is automatically selected when you select the concrete or whatever type material you have. The material types, the HDPE smooth interior, plastic pipe with a smooth wall on the inside. And then the other HDPE material types are plastic pipe that's corrugated on the inside. And then you have concrete pipe, CMP, corrugated metal pipe, and aluminum. You won't use aluminum. Corrugated metal, concrete are probably the ones you're going to use more often. The HDPE, you'll select that and use that one if you are using the CIPP lining. That is a smooth fiberglass type lining in there, so HDPE is a good one to select for that. And then the beveled, here we go. All right, so you have groove end projecting. So a simple cross culvert on a slope, and the end of the culvert is just protruding out the side of the slope. That'll be the groove end projecting or the projecting end. And then you have the square edge with a head wall. So if you have a head wall there and the pipe is just cut off square with that head wall, that's the one you'll use for cross culvert. And it's also the one you'll use for a drainage inlet. So the square edge and the head wall both act as similar. And then the beveled or chamfered, depending on the one you have to select. I'm going to talk about that. Okay, we have a head wall right here, and then a cross culvert going through it. And as the water comes in, it creates a little bubble right here. And so you don't really get as great an interception as you could. And so sometimes if you're not getting enough interception in a situation like this, then you can bevel those corners right there. And it gives you choices between 45 degrees, 33 degrees. And think about the guy in construction. He's not going to get out there with a protractor. So make it 45 degrees and he can guess what that is and get that in for you. So you can bevel these. And then what happens is that bubble goes away and the water just hugs the pipe and you can get a little more flow through the pipe. So if your head water is going up a little too high and you need it to come down just a little bit, you might be able to do that as opposed to going up and adding another pipe beside it or going up another pipe size or so. And then going back to flow mat or culvert master, so that you would select which one you're interested in. Say we'll do the square edge with a head wall here, and then the KE is selected automatically when you select the entrance type, and then the inverts up here. That's the flow line elevation and the flow at the inlet and at the outlet, and then the length of the pipe. And then it'll calculate the slope here for you. And in your spreadsheet, it also automatically calculates the slope. So that's what I use as a double check, just to make sure you got the same slopes there and there are no errors in your input. And then you'll come down and it'll calculate the maximum headwater it gives you the maximum headwater allowable. You've already put that in there. The computed headwater is what the answer that you're looking for. That's the number that we're going to move over to our spreadsheet to make sure it works. The computed headwater has to be lower than maximum allowable. If it's not the end of the world, but don't just accept it and move on. If for some reason you can't get it to go down, then get together with the PE for the project and maybe even bring me in on the conversation. There might be ways around it. For example, you've got a culvert that's 45 feet of fill above it, and you're calculating that that 24-inch culvert just can't handle the flow without overtopping. But in the 30 years or 40 years that that culvert has been in place, maintenance has never seen anything close to an issue with it. So you could use your judgment there, saying that even though the math is telling you that this could be a problem, historical evidence and this situation would say it's okay to go ahead and move forward with that design and leave it at the 2 foot. But you want to make that decision very, very carefully. 99% of the time, you're going to be using the maximum allowable, and you'll just stick with that. So if you have to exceed that, be sure that the PE is involved. The computed headwater, inlet control, outlet control, those are nice to know information, but you won't need it. Discharge and velocity. Velocity is another answer that you're going to be looking for. And if the velocities at the outlet of the culvert start to get above 5 feet per second, then we're going to start looking into whether or not we need to put erosion control out there, RSP, or some other kind of armoring. Or is the channel stable already? And it doesn't mean you definitely need it. What it means is you need to consider it. So if it's 5 feet per second, 5 feet per second or greater. And once it goes beyond 5 feet per second, then you go into the calculations for the rock slope protection, and then depending on or other type of cover for the ground, and you would calculate that specifically. So to get the velocity, that is an answer that you're going to need. Now I can't solve this because I haven't put any numbers in there. So after you give the result here, you want to do an output. And excuse me, I'm going to pause this for just a minute, and I'm going to open up one of these programs or one of these calculations that I've already completed. Okay, here we go. I will go ahead and share now. I found what I needed. So we're back into Culvert Master. So I've opened up one that I've already used as a practice, and going in and filling in the data. And I brought this out of that spreadsheet that I use as an example, I believe, coming down through the circular culvert. And then the first iteration through, what you're going to do is come down. I'm going to have to change one of these numbers. I'll change the flow to 4. Now that I've changed the number, I can hit solve and then come to the output, generate report. Now with the report, it's about halfway down on the right-hand side. You have the critical depth, 0.77. And that is where you're going to type in 0.77 here for the critical depth. That'll automatically add that onto the final tailwater elevation. It takes the 0.77, adds it to the outlet elevation, and gives you the final tailwater elevation. Coming back to Flowmaster, you would add that 0.77 in, and then that would give you your final tailwater elevation right there that you'll use. And then after you do that, solve and generate that report. Keeps coming up now. Oh, there we go. So we generate this report, and then you want to PDF this report and go ahead and save it now. And then in the end, somebody won't be stuck having to come back and PDF all of these at one time. And then move on to the next culvert or the next storm event that you need to look at. You want to do this design for the existing and the 100-year are existing and proposed for the 10 and 100 year. And then the final answers that we're getting out of here. The final answers come into as the computed headwater and the critical depth is if necessary, and then the velocity. And then finally, there's a couple of notes right here. You can refer to these notes down here. They're kind of the standard ones that you might use, or you can add or change these as needed. And the available headwater taken from field observations, for example, it lets them know where you got the information that you're using here. And with that, I think we're done with the presentation, and I think I saw Sung Ho had a question.